So that's fine. I think Kriti Marwa has done maths, is it?
Yes, sir.
Yeah.
I had
So
did my bachelor's.
yeah, so I think Kriti will be able to, kind of identify with some of the things. But what I want to know, what I do want to share with you is that I think there are 18 people in the room. So there are lots of equations that will come your way in when you treat derivatives, okay, or when you start to talk with derivatives, when you start to use derivatives. Uh, Even myself, like I've literally like used it quite a bit, but now I should confess and I should tell you if it is kind of it could pacify your anxiety, that although maths is required, it is not much, you don't get inside maths. What I will try to tell, or what I'll try to share, is how to get a profound conceptual base without getting into the weeds. You will be a practitioner if, as a practitioner, you'd like to know the broad concepts of what is going on, but not necessarily going into integral calculus or derivative calculus. So that's what we'll do. We'll give you some conceptual background of what this is, keeping the maths to the minimum, and then we'll start playing around with the Greeks. Start playing around with the options. Any questions so far?
No,
Okay,
sir.
let's begin. I mean, how many of you have Python background?
So we all have did a course in business analytics last year.
Okay. Uh, okay, so and that covered Python, is it?
Yes, sir.
So just the basics, and you use some libraries, so that's all.
Okay.
Not much.
So I guess what you can do is, I mean, the course is probably uh, a good place for you to not just get some basics on derivatives, but also really brush up your hands with and minds with Python. Okay, so let's begin now. I am trying to do a slideshow. 1 second. You're able to see my screens, right? Are you? Hello?
Not yet, sir. I'm not sure if you've presented.
Oh, okay. Sorry. Yeah, I need to present this. So I am presenting the. Okay, you can see my screen now. Hi guys, can you see my screen?
Yes, sir. It's
Yes,
visible.
sir.
Yeah. Okay, so let's begin. Uh, this is a typical call option, right? I mean, you can see on the x-axis you got the strike price, and on the y-axis there's the price of the option. And as you can see, this is a TCS. The stock price, the stock is TCS, Tata Consultancy Services. And what is the payoff diagram at expiration, right? So here in this area is the strike price, and as you can see, after the strike price, you start to get a positive payoff. And what you pay here is the premium, right? Everybody is familiar with that. To know, can you all take a poll? How do I do a poll here? Can somebody tell me, like, call options are in the money, right? When are call options in the money? Option A, if the current price is above the strike price. Option B, if the current price is above the stock price. C, if the current price is below the strike price, if the current price is below the stock price. How do I administer this option, this poll?
So you can come to your Google Meet. Then there'll be like a Squid Games kind of activities out there: rectangle, triangles, circle. You might want to
Yeah,
use it.
yeah, perfect, yes.
And
And
then
then,
I'm not sure after that because I've never used it past.
perfect. Thank you, Neil. Thank you very much, Neil. So this is the only way to keep the class engaged, because otherwise we will not know what is going on in I would love to actually do this online. Many of you know this answer. Actually, from the next time, can Neil, can somebody do a pre-prepared polls? Like, I can give the poll questions in advance, and can somebody from the class actually administer it well in
Sir,
advance?
I don't think we have the access to do the polls.
Okay, because that's a question I asked yesterday, but nobody really responded. One second. So now here it is, and I am starting the poll. Okay, can you saw the poll? Okay, 3 votes so far. Are others voting? There are 22 of you. Seven votes. Ten votes. All right, I want to go beyond at least half mark. Okay, we have got 14 votes. So others are voting. I don't know if others want to vote, but there's 15 votes now. So those who have got it right, I mean, if the current price is above the strike price, that's the right answer. A few of you have not got the right answer. Maybe it's just a play of words. But I hope your fundamentals are clear. That is whenever this is the underlying stock price, right? Whenever stock price goes beyond this, then the option is in the money. Okay, the option is in the money. This is the area where it is in the money. Okay, so let's move on. Let me know if you're not able to see the screen. Okay, so now the second poll. End the poll. While I'm writing these things, can somebody guess why is the option in the money if it is above the strike price, and why it is called so? Can somebody volunteer?
The call option gives a right but not an obligation to buy a specific security at a specified price. So if the current market price is above the strike price, it is in money because you can buy expensive things at a cheaper rate.
Perfect. Yeah. So I've launched one more poll. Call options are in the money if the current price is above the strike price, option 1. If the current price is above the this is still the intrinsic value of a call option is difference between stock price at inception and current price, difference between stock price and strike price. Slightly trickier question. Yeah, most of you have kind of gotten it right. It's the difference between stock price and strike price. So that's the intrinsic value of an option. Now I've a little bit better idea of where everybody is in terms of calls and options, right? Let's go to now I'm going to bear with me. We are going to go into maths. Okay, so the next 20-30 minutes or so, maybe more. We are going to go deeper into maths, but I promise you that it won't be overwhelming. So it starts with Robert Brown in the 1800s, right? Robert Brown was a biologist. And what did Robert Brown do? He would do what a biologist would do. So he was observing, pollen, and he was observing these particles, and these are really, really small particles. And he was seeing that, without any force, these particles were moving around randomly. Okay, so they were just moving around. That word random is also a very loaded word. And I would like you think of what random events you've seen. But coming back to Robert Brown, so he was observing these things, and he was seeing that these particles are just going around everywhere. And in the 1900s, right, there was Einstein who dabbled with this, but Bachelier, he was a French mathematician. He was the first one who actually applied it to the stock market, the Paris Stock Exchange. Not talked about much, but he did quite a bit of work. And then after that, we had Wiener and Levy. Wiener is a mathematician, and all of both of these people, they started to. There's a proper Wiener process. In fact, many of the things that you see, including talking on mobile phones and stuff like that, and especially cryptography. So you can give the credit to these people. So these are the ones, So Robert Brown started the Brownian motion. And why are we talking about Brownian motion? Because there's a connection from Brownian motion to Black-Scholes. There's a connection, and you can see the how history has changed. Like everybody is standing on everybody else's shoulders, right? So Bachelor and Einstein, they stood on the shoulders of Robert Brown. Wiener, Levy stood on the shoulders of these guys. Ethos area was very, very different. He was not really concerned about financial markets, but he was the first one who took this area of study called randomness or stochastic calculus, and he married it to the normal calculus. So there's something called as Ethos lemma or Ethos rule. And finally, you had Merton, Black, and Scholes in the 1970s, 1973 to be precise, where they came out with this famous equation. Actually, Merton and Scholes were there, but Black, they got the Nobel, but Black was already, he was no more by that time. And so that's the brief history of Brownian motion. There's a good book in the syllabus. I saw Professor Panda has recommended a book. That book is a bit heavy on maths, but if you actually Google around, including a book here, I don't know if you see this book. Can you see this book? Can you see this book? All of you, those who want to really, practice options trading in practice. Sorry, I can't. Are you able to share my? You can't see the book, right? Are you? Hello? Can you see the book?
So we can see it. Franz the Earth and options.
Yeah.
The options trading.
Yeah. So this is a very practical book, and this book is it's very old. I used to use it on the city trading desk all the time for referencing, and I don't know. Maybe it's now. By now it is free. Actually, there's Nassim Taleb's book also on options, on specifically on dynamic hedging. That has got a bit of maths. This book doesn't have that much of maths, so it's much more consumable. So there's a lot of history. To sum it up, there's a connection between Brownian motion on one side and Black and Scholes model that we see today on the other side. And I just wanted to kind of pay the respect to all these people who have been behind the scenes, and all we see right now is Black-Scholes. So when you apart from Kriti, who's got a very good grounding in maths, I think for most of you probably this is going to be a foreign language, right? All of you are familiar with calculus, right? Most of you will be familiar with calculus. Calculus has its boundaries, because Newtonian calculus is, or Riemann integrals as they call them, it is to do with a certain set of processes. But stochastic calculus is an entirely different area where we talk about random variables. So that's the stochastic calculus part. The third part is Ethos rule, which tries to marry stochastic calculus to normal calculus. And lastly, based on all of this, we come up with the derivatives pricing model. Everybody's clear to this point? We have not talked anything yet, except
Yes. So we're clear, but your PPT is frozen. We are still seeing the first poll.
Oh,
Not sure
really?
if you've changed the slide.
You're not seeing the slides at all.
No. What we are saying is the first slide where you've written poll 1, right? That's what we're seeing as of now. I think you'll need to
Oh,
present your screen once again.
I need to do what? Sorry, I need to.
I think you'll need to present your screen once again, and this time use the option to present your entire screen, not just a tab or a window.
Yeah, let me do that. Let me do entire screen. I mean, that's better. Now you can see the entire screen, right? Now you can see the thing.
Yes, sir. That's good.
So this is the second one. I mean, this was the first one where I was saying that this was Robert Brown. This screen, probably you have not seen this, right? Thank you for pointing out. You have not seen this one, right?
No, so we're seeing it for the first time.
Yeah. Okay. So this is what I meant by Robert Brown, who was doing in 1800s, and then Bachelier, who started with the Paris Stock Exchange, Weiner and Levy, cryptography and stuff like that. Weiner's, we call it as a Weiner process, but Weiner is more known for cryptography, but he contributed to this. And then there is Ito, and lastly there's Merton, Black and Scholes. Okay, so that's the history, and that history is reflected in this kind of this block diagram where you've got 4 big blocks. So I wanted you all to think about the maths in derivatives as divided into 4 distinct sections. The first section is calculus, where we are talking about derivatives and integrals. The second section is stochastic calculus, where we are taking we are talking about calculus of random variables. Okay, so it's kind of I don't know whether we can coin that term called calculus of random variables, but that's what it is. And the person who made many parts of this responsible is, his name was Ito, and that Ethos rule plays a bridge between normal calculus and stochastic calculus. So I'll come to that. And then based on all of this, there is a derivatives pricing model, Black and Scholes derivatives pricing model. Okay, so that is what is reflected in the last slide here. In this slide, this is what is reflected. Robert Brown was credited to the term Brownian motion, but it's really started from Bachelier and Weiner, and then it went to Ito, and then it went to Merton, Black and Scholes. Okay, everybody clear till here?
Yes, sir, clear.
So nothing really. This is just a conceptual pathway. If you at all go for a deriv role in a bulge bracket bank, at least you should know these terms, right? I mean, you should have heard about these terms. If you're going for a trading desk role, I have not known anybody in Citigroup. Sorry, not Citigroup. I have not known anybody in markets over here on the derivatives desk who are as familiar with the maths, as perhaps I am right now. And there's a reason to this, because in practice, what happens is you look at very, very few terms, you assume certain things. And the more you use computational finance, you'll have to, for example, assume many things, including supply demand is right. You have to assume those things, right? Understand what they are, but assume that they are right. So I just want to, get our current familiarity with calculus. Okay, so that will end poll, new poll, my familiarity. Sorry, just give me a minute. I need to get the door. Sorry, I had to attend the door. So my familiarity with calculus is on scale of 1 to 5, 5 being highest. 1, 2, 3, 4, 5. So can you quickly, answer these things? It's a simple question. Okay, so many people are, kind of like on average familiar with calculus, which is good. There are some of you who are not. So let's go ahead. Thank you for the response. So let me just, in any case, let me just refresh what we're really talking about, right? So this graph is, by the way, generated in Python. As you can see, this is a simple curve, right? And what is a curve? It is, this curve is defined by this expression 4x square plus x plus 1. That's the red curve, right? I mean, it is symmetrical kind of, in these two quadrants, on the positive side of the x-axis as well as the negative side of the x-axis. So what is the derivative of the curve? The derivative of the curve is just the tangent at this point in time. It's just the tangent to this. And, you can get the equation for that as, and nomenclature is f prime x, or f, the derivative of x, which is 8x plus 1. So what do? You do 4 to the 8, and then you do 8x, and this is n minus 1, so 8x plus 1. So that's the derivative, and this becomes 1, because this was 1 minus 1 is 0, and this becomes here. So, so that is why you get a 1, and the derivative of this is 1. The concept here is, what is the derivative? The derivative is the tangent at any point in time to the curve. So suppose you wanted to know, the derivative at this point in time, right? This point in time. So what we are trying to do is, we are drawing a tangent and getting the slope. Why is this important? Can somebody tell me why is a derivative important? What property of derivatives do you use? You're able to see the graph, right, by the way, or is it?
Yes, so we could see it. Now we can see you.
Oh, you are not able to see it.
Yeah,
Sorry,
we could see it. Yeah.
You could see it. So can somebody tell, why are derivatives so important? I mean, I already, kind of gave a part of the answer. Like, if I wanted to know the slope here, I know the derivative. I need to find the derivative. But what does that signify?
So it helps us find how something changes with respect to something else changing.
Fantastic. So that's what it is. So we need to know, how fast something is changing. And what do you mean by how fast what is changing? The person who answered, or somebody else can try. Was it Neil?
Yes, it was me.
Yeah. Somebody else wants to attempt that. Why are we interested in knowing how fast is something is changing with something else?
So may I?
Yeah, sure.
So at the end of the day, we are trying to figure out if we do something, what are the consequences of that. So assume that assuming that we can figure out what is the functional form of a certain thing and theorize on it. And if we make some small change in our behavior or make some small change in a certain thing, it gives us what may happen to the thing that we are trying to see.
Correct. So I don't know if you've learned machine learning. I mean, that's the kind of the answer. But what happens is that, all the time in financial life as well as day-to-day life, what we are trying to do is, we are trying to get a function of something, right? So in this function, we call fx as the dependent variable, right? The dependent variable. And we call x as the independent variable, correct? So all we're trying to do is, suppose we call f of x as y, and y is dependent on x. We want to know, by changing x, how much is y changing. Suppose somebody came and told you that the stock price for TCS is dependent on how many times the CEO is going to the US. Let's just say, right? I mean, let's say we form a function, the number of times the CEO is going to the US, which is X here, the independent variable, and the stock price as the dependent variable. And then we formulate the equation, if at all there is an equation. And if that incremental change by the CEO going to the US, is it going to increase the stock of the value of the stock price, which is given by FX? So that is why we are interested in this type of thing. We are not interested in the slope or what this f prime means. This is just a nomenclature, right? The f prime x is just a nomenclature, or the derivative is just a nomenclature. We are interested in the rate of change. So let's go on to the next slide. Now, when we come to partial derivatives, what we are extending now is that we are, instead of having one independent variable, we are having two independent variables. Now, what do we mean by two independent variables? Suppose we are saying that not only is the share price for TCS dependent on the number of times the CEO is going to the US, it is also dependent on, let's say, the growth rate of banking, finance, the BFSI sector. Are you all with me? Why am I saying TCS CEO going to the US and the stock price has a correlation? Why am I saying that? Anybody who is holding TCS here, or anybody who knows what TCS is doing? I want you to think like practitioners, because maths is one thing. I want you to apply. I'm hoping that you can apply what you learn. Yes.
So may I try?
Yes.
So from what I read in the news, they are in talks with Microsoft or some other big tech company for some. There's some collaboration that's ongoing.
Just give me 1 second. Just give me 1 second. Sorry. Ali, please go on. I'm sorry about this.
Yes, sir. So what I was saying is, from what I read in the news, TCS is in talks with Microsoft or some other major US entity for some big project. So there's a lot of positive sentiment around that.
Yeah, correct. So I mean, I don't know if you started looking at balance sheets and annual reports and what are the revenue attributions of a company. But if you see, many of the software companies in India, a bulk of the revenue comes from overseas, right? So, and US is one of the major revenue generator for TCS. And another major bulk for software companies, it comes from the growth in the BFSI sector. So that's why these two are, like I was just saying, I'm just making it up. Okay, nothing. Everything I'm saying in this class, nothing is actual. I'm just trying to make up. I'm trying you all to think both as academicians but also as practitioners, so that what you're learning is not just plain numbers and Greeks and stuff like that. You can use some of these things to think what is happening in the real market. So these are the two independent variables, the number of trips to the US and the growth of the BFSI sector. Suppose I say that my stock price is dependent on this, and I try to plot x square plus y square. And in the last slide, you saw that a simple thing is a parabola, right? Is a kind of a parabola, but this parabola is a line, right? It's in 2 dimensions, right? There's an x and y axis. But what happens here is there are 3 axes. there is X, Y, and Z, which is a dependent variable. Are all of you with me? Now this has become a parabolic plane. Okay, so you can see that it's a contour, right? And this contour is giving you, it's saying that as these guys increase, as the number of trips are increasing, as the BFSI sector is increasing, the stock price is just going to have fun. It is going to increase in all directions. Okay, so if it were to increase in this particular direction, X is going to increase more, or Y is going to increase more, or whatever. Now, if you wanted to have, now how do you think about these things? Like, suppose you wanted to know what is the incremental trip for the US that the CEO is doing. What is the change in the stock price? Suppose you wanted to know that answer to that question. What will you do? Anybody? The incremental change. In the last slide, we saw that this is the change. This is a change, a small change in dx is giving you the change that you have in dy, right? The f prime x. That is the interpretation, right? So what is the interpretation? A 1 unit change in x. Suppose x moves by 1. How much will y move by? 8 into 1. That is 8 plus 1, 9. That's how huge the change is. Correct? Now, similarly over here, how do you interpret this? Can somebody share?
Are you asking about the red plane?
I'm asking that there are these two variables. The first variable is the number of trips to the US of any company, not just TCS, any IT company, because IT seems to have a really good bonding and dependence on the US. And the second thing is the growth in the BFSI sector. So 1%. Yeah, sorry, go on.
So basically, the blue and green one, that gives us the stock price, assuming dependent on the x and the y that you have said. From what we can understand is at 0, 0, 0, at 0, 0, it will be the least, and it'll keep on increasing by squares along both the axes. Now
Correct.
The thing is that the red plane tells us the derivative at a certain point and according to a certain plane, according to a certain variable. So that plane out there is the partial derivative with respect to one of the variables, and if we take it from the other direction, 90 degrees from that will give us the partial derivative from the other variable's perspective.
Correct. No, so that I got, Neil. I think, was it Neil who answered it?
Yes, sir.
I want to understand from from you or someone else, what does it mean? Like we saw, I mean, the derivatives part I understood from what you're saying. What does it mean?
So as we increase the number of trips to the US, I think that's what you mentioned, X was,
Correct.
the price will probably perform better. Same with the industry. The more you do it, it'll improve. But actually the thing is also, if the number of trips decrease, even then it'll increase, because it's assuming you're saying it's still X square.
Correct. Yes.
And the
yes.
same, even if the industry does worse, it'll still. So as long as we are in this, nothing happens, we are at the same place. But in any direction, it'll move. It depends where we are right now. That's all.
Yeah. Good. So now you're thinking, Neil. So somebody gives you an equation, right, and gives you a derivatives and saying that apply it to finance. This is how you have to think. Good that you have thought that even if the trips decrease, actually the incremental trips decrease, this function is actually going to give you a positive stock price, which is not correct. So you can see through, and you're absolutely right that this plane is as if you're standing on one side of the axis and then seeing how fast is the y changing, the z changing, how fast is the stock price changing. So that's the only thing about partial derivatives. There's no mumbo jumbo. What you're doing is you're putting one, suppose there are 3 variables now instead of 2. I have added one more variable. If I want to know the change of this with respect to this, all I can do, as a sane person, is to keep these 2 guys constant and then see what is the incremental change in this if I change this. Okay, so that's the interpretation of that. What you missed to say, Neil, is that when you do this, you have to keep these guys as constant. You don't change those guys. Okay, so this is the marginal change. What is the effect of the marginal change in X or the trips to the US, given that the BFSI sector growth is constant, what is the marginal change in the stock price if there's one incremental trip to the USA? Okay, and this, by the way, both of all the graphs that I'm doing, they're all done in Python. I would like you to embrace Python like nobody's business. You can see this is industrial quality graphs, right? I mean, even the textbook graphs are not as good as this, because probably the textbook graphs were done in Excel. Let's go to the next one. I think I'm spending time on poll, and I'm just losing valuable time. So by the way, this is a quadratic equation, right? And what is quadratic? As you get higher orders, this is the order of an equation. This equation is of order 1, right? So we don't have higher order. This is the order 2 equation. So polynomials are higher order equations. Like whenever this is a quadratic equation. I'm asking you guys, what is the partial derivative of this with respect to the first variable delta x? Which one of this is right? Can somebody tell me?
Sir, I may be wrong, but I don't think any of these.
Who's that?
Me, Neil.
Does anybody agree with Neil or disagree with Neil?
Sir, agree with
Yeah,
me.
Agree with Neil, sir.
Yeah, you're right. You're right. That's correct. So what's the right answer?
Sir, I believe the answer should just be simply 2x.
Correct. That's right. So why is it 2x? Because there are simple rules of derivatives which you can do, and you can actually hand calculate them. Even when these are the simple derivative rules. But I would encourage you for making maths fun. You can hand calculate these things. You can draw these graphs, create a table in Excel, and then just check what is happening. Just check what is happening. You'll find out that the rate of change is what you get. Okay, so this when you go into deep maths, right, this will stand you in good stead, because then you'll realize that the equations that you're seeing on screen, or when you are actually looking in a textbook, these rules come into play. I don't want you to memorize them, simple rules, but that's what it is, right? We'll have to use them. You can't go back to Excel, or you can't go back to Python every time to find out what is really happening when I say x square plus y square and try to take a slope of that. Okay. So these are derivatives, refreshes a cheat sheet. Now we talked about derivative calculus, right? Now we are going to integral calculus. And what do we do in integration? In integration, we do the reverse, right? We say that this is the x-axis, this is the y-axis, and then we plot the curve. And after plotting the curve, we want to know the area under the curve, right? We want to know the area under the curve. So what is this curve? Is anybody familiar with this curve? What could this curve be?
Bell curve.
Yeah, it is a
Sine
bell
curve.
curve. You're right, Neil. It is actually a sine curve. It is actually a sine curve. I have not drawn the the lower half of the sine curve, right? So and if you wanted to integrate between two, so in integration, if you recollect integration, right, not much of integration is there. Although you'll get to know more of integration when if you try to go deeper into the math of Ethos calculus. But what this integration does is that you can integrate from one limit to another limit. Here I'm integrating pi by 2 to pi, right? Pi by 2 to pi. Pi. What is the value of pi? This is in radians. Okay, so 360 degrees forms a circle. 360 degrees forms a circle. 180 degrees is the pi. Okay, and the full circle is formed by sine curve. When it goes from this end, it goes this way, this way, this way, comes back again. Okay, all of you with me? Anybody, any questions? I guess there are no questions, right? So this is the integration part of in between, and I'm saying integrate between pi by 2 and pi. So if you actually integrate the sine curve, sine of x, and you do you give the limits as lower limit as pi by 2 and the higher limit as pi, you'll get this shaded region, and then you can actually get an area of the curve. So now let's go to to the heart of these things. This is all of you know that the are you all familiar with this first equation? PT, the price of suppose you put some money in the bank account, right? You put money in the bank account. Let's say you put 100 rupees in the bank account, and 7% is the interest rate for those 100 rupees. What will you get after 1 year? ₹100 I put in the bank account, and 7% is the interest rate. What will I get after 1 year? Anybody?
So 7 rupees.
Sorry?
7 rupees interest.
So you will get, Prasoon, you'll get 7 rupees as interest, right?
Yes, sir.
But what will be there in the bank account?
Minus TDS.
Yeah, correct. Now you're thinking too practically. You're right. So the bank account will contain 107 rupees minus the TDS, which is 10%. Correct. So how do you get this value? Right? This 7%, how do you get this value? You simply did, 100 and 7% is the interest, and we blindly took that, right? But what if now, I were to say that, in this case, I were to write the equation. The final value in the bank account is the initial value into 1 plus r divided by n and raised to n by t. Now, suppose n is kind of 1, right? The number of periods is 1, and here it is 1. So I just do a multiplication of this. So this is 1, this is 1, this is 1, this is 7%, this is 100 into 1 plus 0.07, and I get 107. Everyone clear with this? Hello?
Yes, sir. Yes, sir.
Yeah. Now imagine that I have divided this 1 year period into 12 different periods, like 12 periods. So first period I actually go to the bank, I put I put the 100 rupees. On the same day I take back the 100 rupees, I again put the 100 rupees. So I do that silly thing every 12 times in a year. And then if you try to calculate this and put n is equal to 12, n is equal to 12 over here, and you actually calculate this, you'll get an exact answer again. Okay, so you'll get again the 107 value. But now what we are doing is we are using this formula really of continuous compounding. So in the bank account, if you put in the value, if you do an integration of this and you find a curve of this, the curve area under the curve, you'll get this value. That is where you start to use, that's the thing that we are using in practice, right? We are starting to use calculus in practice. Everybody clear with this? Anybody who is not clear? I've done nothing. I've just said we put money in the bank account, and how do we get, like, instead of a full year, if you put just 1 month or 37 days or 15 days, what do you get finally? Anybody unclear? I'm asking this because
Yes,
some of
sir.
you,
Yes, clear.
you're clear, right? Thank you. See, guys, please keep talking. Otherwise, I don't know. I was also a student, so I know that, and I was a backbencher. So, we would throw rockets and stuff like that. We are not in, real life. I'm just talking with you on the screen. So I don't know if I'm talking with myself. So, and if I'm talking complete gibberish, you need to alert me. Now we go to this thing called as a log normal distribution. And I'm using two terms over here, right? Log normal and distribution. So what is a distribution, and there are different types of distributions. Okay, so I don't have a chalkboard, so I'll have to use this to denote what I'm saying. So what is a normal distribution? I want to show what is normal distribution. And why am I doing this? Because this is, I'm sure you would have done it hundreds of times, right? But this is the most important concept in in not just in finance but in real life. Okay, so this is the normal distribution. Can somebody tell me the key characteristics of a normal distribution? It's the bell curve. Somebody had told me that this is a bell curve. The bell curve. Anyway, sorry. So
Sir, all the numbers lie within the standard deviation 3 on either side.
okay, so this is the standard normal distribution, and this is how it looks like. So let me take this. Okay, this has got some very important properties, right? This is a normal distribution. This, and what do you have here on the you can see my screen, right? All of you?
Yes, sir.
Yes. So you can see that you've got the y-axis and the x-axis. This is called as a histogram, right? A histogram. And in the normal distribution, you got the mu as the mean, correct? And you got on the left hand side of the mu and the right hand side of the mu, everything is spread evenly. And this probability density is nothing but the number of observations. So you can actually start rolling the dice, or you can there are many other real world examples that you can take. And when you start rolling the dice, what you will realize that your throws will form, the number of times you get a 6 will form a normal distribution. Okay, and that's where central limit theorem comes into picture. There are some very key characteristics of the normal distribution. So this is one standard deviation is nothing but the volatility. The volatility of this thing, how much does it move from the mean, right? How much does something move from the mean? How much does the observation move from the mean? Okay, that is nothing but a volatility. And this volatility is, is measured by standard deviation. So this is 1 standard deviation, 2 standard deviation, 3 standard deviation. And within 3 standard deviation, practically all the values that you would have known historically are captured by the normal distribution. So that's the normal distribution for you. Okay, and you'll be using that in the Black-Scholes model. Okay, you'll be using that in the Black-Scholes model again and again. So you need to be very clear on what the normal distribution is, and not just the Black-Scholes model. You'll be using normal distribution in machine learning anywhere and everywhere you go. Be extremely clear about that. What the log normal distribution does is something else. In the log normal distribution, what we do is we take the stock price S of t. Okay, we take the stock price S of t, and what we say is the log of the stock price. The log of the stock price is normally distributed. Are you all with me? Anybody with? Yeah. So the log of the stock price has a normal bell curve, is what we are saying. And why are we saying log? Because the stock prices, can they be below 0?
No, sir.
They cannot be below 0, right? That's the property that we are using, and that's why we are using the log normal distribution. So logarithms cannot be below 0. So log normal distributions become really, really very useful and handy. And it just so happens, now I'm going into the heart of stochastic calculus. What it says is that the stock price log of ST is defined as log of S0, the starting price, plus this term over here, which is defined by mu. Mu is really the expected return. Okay, just think about mu as the expected return, minus 1/2 of the standard deviation, the square of the standard deviation. Just absorb that. Okay, we'll not go into the maths. Just know that this is what it is. This is how stock prices generally behave, and that is why this equation is. So it's nothing but log of ST is equal to log of the stock price at any point in time is the log of S0, the starting stock price, plus a term which is driven by the mean minus 1/2 of sigma square, the variance, and that as a function of time. So as time passes by, I'm going to take, so suppose I'm in the second year, or it's counted in days actually, or let's count it in years. Second year, third year, so this is 3. The mu is, let's say the expected return is 15%, standard deviation is 25%, you get some value over here. You add that to the to log of S0. And then this is the random term. Okay, so this is the term which is the random behavior which we are capturing by as sigma, that is standard deviation, root of t. Okay, now I'm taking the root of t and zt. Now zt is the normal distribution. It is, it can be anywhere, right? So I'm saying that at any point in time, suppose I were to predict the stock price 3 years down, what is my best predictor? This model is saying my best predictor is the beginning stock price, and some function of mu and sigma, the standard deviation and volatility, which is scaled by time t. I'm scaling it, right? I'm just scaling like suppose I say instead of 1 year or 2 years, I'm saying 3 years or 10 years. Now I'm scaling it by 10 years, right? I'm scaling it by 10 years. And then I'm saying this is the term where I really need to worry about, because this can be anything. Why can this be anything? Because z of t is a standard normal distribution. And what is the standard normal distribution we saw? It can be anywhere here. It can come anywhere here, right? And I'm multiplying the value of zt by the root of t again. I'm scaling it again, and I'm multiplying it by the variance. Sorry, the standard deviation. Everybody with me? Any questions? Any questions? Sorry, I hope I have not put you off to sleep.
No, sir. No questions.
No questions, right? So just take it at face value. Just take it at face value, and I appreciate you taking it at face value, because that's what it is. Assume that some great scientists and mathematicians, they spend days and night together and they came out with this. Assume this to be true. Now, if I want to just get the stock price, what do? I just take S of t and I do, I'm just taking a inverse of this, right? How do I do an inverse of this? I do an inverse operation. I do exponential, so I get a S of t, and then I say S0. So this is my stock price. So expected value of S really is S0 into e raised to mu t. Makes sense, right? So expected value of my stock price at any point in time, I say, is the starting value. Suppose you wanted to forecast Nifty. You could just say Nifty is the value of this, the Nifty value today, and then just say e raised to the mean value, the mean return of Nifty multiplied by time. So that is my expected value of the Nifty index or anything that you can take. And what is my variance? You can calculate the variance quite easily, actually. The variance term, you can calculate the variance here very, very easily. Just say simple maths. You say log of st minus log of s0. So that is how you get log of st by 0. And then the variance of this is just a deterministic term. So this will be, the entire thing will be 0. This term will be 0. And now this term, what I do is I square it. Since it's a variance, I square it. So I'm saying square. So this root of t becomes square t. Just t. I get it over here. So this becomes 1 by t. And then I say that rho of this, the standard deviation of this is nothing but 1 by t variance of log of st by s0. And why is that? Because zt, remember the property of the standard for the standard normal distribution variable. What is the property? Mean 0, variance 1. Are you with me? Right? Becomes
Yes,
very
sir.
handy. Now, since the variance is 1, this becomes 1. So I get the standard deviation as 1 by t into variance of log of st by 0. So that's the variance of my stock price. It makes intuitive sense also, right? Intuitive sense also. So at variance of the expected variance at any point in time is nothing but the st by s0, the logarithm of that, and the variance of this term, right? What is the variance? So I take bunch of values, calculate the variance, and all of that scaled by 1 by t. Any questions so far?
No, sir.
Hello? Yeah. So put your seat belts on. Don't question too much. Just accept what it is, and let's move on. Okay. But what I would like you to believe is that these things have been proven again and again by mathematicians. They may not be true. So suppose you actually take the value of TCS right now here, you might say, okay, then it's very easy. It's so easy. You're giving me everything. You're giving me mu. You're giving me this. You're giving me this. So I can find out what is the value of my TCS stock price or Infosys stock price in 1 year's time, right? You can literally find that. And will you then bet on it? Can somebody say, tell me why will you not bet on this equation? Anybody?
Sir, efficient market hypothesis states that it is nearly impossible to predict future stock market prices. So I'll be hesitant. Those two equations are against each other.
That's correct, but that's one part of it. Correct. I mean, you're talking about rules right now. I'm just trying to ask, trying to nudge you into thinking. What are the logical reasons you won't believe in this? That is one logical reason based on what you've learned so far. What is something that can actually dismantle the cart here? Suppose you know nothing about efficient market hypothesis. Just look carefully at this term. Where do you get the randomness in this?
So which term are you pointing at? We cannot see.
So this one, right? Suppose you, in fact, you've got a small Python program that you'll be practicing to predict the stock price. So all I'm saying is that you take any value here, you know the value of S0. Let's say, which is your favorite stock? I don't know who I'm talking with. Which is your favorite stock? Sorry, can you tell me your name?
So my name is Neil.
Yeah, Neil. So which is your favorite stock?
Sir, I don't have a favorite stock, sir. But we can take TCS for example, sir.
Okay, let's say TCS. Suppose you want to predict, can you predict the price of TCS based on this?
Sir, I presume no, sir.
No, I'm saying based on this equation, like you've got everything, you can put it in Excel and predict it, right?
Sir, let's say the variance, the standard deviation, we are not sure for how many terms we should take it and so on and so forth.
No, I'm asking Neil, like you're an analyst and but a mathematician as well, and just based on this, I'm asking you to give me the value of TCS in 1 year's time. Is that possible?
Sir, again, I would like to repeat my point that when we take standard deviation, how many terms previous standard deviation should we be taking? So all of these things will keep on giving me different answers.
So correct. That is one source of uncertainty. Suppose you got both this and this. But what is the biggest source of uncertainty in this equation?
I'm not sure, sir.
Okay, so this is ZT, right? That's a random variable.
All right, sir.
You see what I'm saying, right? So when you actually, that's why, I've got this exercise where you'll put this in practice, where you'll see why the uncertainty, even through this mathematical equation. This is a mathematical equation. So every time you run it, it will give you a different value. Okay. We'll come to that later on, but that's the source of uncertainty. In addition to, other things that this equation itself is questioned. So let's move on now. Let's go to the basics, really basic definitions. Now, I would like you to, like we talked about log normal, I would like you to, acclimatize yourself with these basic definitions to what they are. Let's not worry too much about, what they mean and the maths behind this, which we will unravel in the, forthcoming slides. What I would like you to understand is, or familiarize yourself is with terms. The first term is stochastic process. Okay. What is the stochastic process? This will come again and again and really bother you. Stochastic. Bol kya raha hai ye? So stochastic process is nothing but, if you've got random variables, that's it. No mumbo jumbo, it's a random variable and that's why you have a problem. And how do I define a stochastic process? Let's say this is TCS, right? TCS in time t. And, for all time t, the values that I get for TCS stock price And each and every state of TCS stock price, not just day to day, day 0, day 1, day 2, day 3, day 4, within the day itself, right? You know that stock prices run by ticks, right? You're aware of that, right?
Yes, sir.
Hello?
There are certain tick sizes that
Exactly.
have to.
Yeah. So every single tick that you see, one tick, second tick, third tick, infinite ticks, all of those ticks are random variables. They are independent of each other. Okay. So that is a stochastic process. Be very sure of this term. Now, stochastic process
Could
is
you
one
please
thing.
could you please repeat that?
So TCS has got stock prices, right? What you're seeing as a stock price, you could have, let's say, 3,500 here, 3,600, 3,601, 3,602, 3, 4, 5, 3,700. So all of these are ticks. They are x of t, xt1, xt2, xt3, xt4, so on, right?
Yes, sir.
Right? So all of these prices, actual prices, they are independent of each other. They are independent random variables. I'm making a
I
statement.
mildly disagree on that, sir.
No, correct. So, sorry, is that Neil?
Yes, sir.
Yeah. You're right. You can actually fully disagree on it. That's why Warren Buffett is in business, right? And that's why many people are in business, because they completely disagree with that. What I'm saying is, I'm giving you a definition of this term called as a stochastic process.
Oh, okay, sir.
Okay.
Sir, I had a query.
Yeah.
Sir, you're stating formula that's okay, but let's say recently AMC and GameStop stocks were in news, and they went through the roof basically because some random people on Reddit decided that they had enough of corporate overlords ruling them. So basically, is there mathematical formula used practically, or it just theoretical sense?
Sorry, I am not able to see your name. Who is this?
Mihir.
Yeah, Mihir. So we are trying to use concepts here and not practice. You're absolutely right on Reddit, and earlier on, Neil was saying that I disagree. He mildly disagrees with it. Actually, he can fully disagree with it. So what happens is that you don't know how sunlight is reaching us, right? Sunlight. I'm saying, I'm not even talking about stock prices. I'm talking about natural phenomena. People all the time, physicists, they're trying to model things. And through models, like gravity is one model, right? Things are falling down. You can see that. You can just take a pen or a mouse and it is falling down. So the conceptual basis for that is that there is gravity and gravity is pulling it down. All I'm saying in this equation here, the log of st, that somebody came along and said this is one conceptual basis that you can take. That is all I'm saying, nothing else.
Okay. So this is the best fitting model we have right now. Basically, we can say that.
Yeah, so this is one model. Like, you're trying to do a maths on this, right? There is nothing guaranteed. You're trying to do some maths on this. You're trying to predict prices. In fact, when you go to recurrent neural networks, all of this will go for toss, because you won't know what those neural networks, what equations those neural networks are forming. And those will actually change not only from stock to stock, but time to time. Okay. But let me not go into machine learning. All I'm saying is, hold on to this equation. This is a log normal distribution, and this is how I am treating the stock price, is what I'm saying. I left you at that on this slide. I said bye, forget about it now. Park it in your brain somewhere that there's a log normal distribution and a stock price could be predicted. You all are with me, right? Hello?
Yes, sir.
Yeah. The next slide, what I'm saying is, I'm actually now going into for a moment, forget about stock prices. I'm saying, what is a stochastic process? A stochastic process is a process that creates a range of values, one after another. Suppose, you take a ball, right? You take a ball. Many of you may be playing cricket, and you're just, thumping the ball up and down. or you take a, if you're a squash player, you take a badminton, you take the squash racket and put the ball on the, smash the ball on the thing and keep on smashing it again and again. So the length of the ball that is coming back, let's say, L1 is the first length, L2 is the second length, L3 is the third length, and so on. All I'm saying is, in a stochastic process, L1, L2, L3, L4, L5, L infinity are independent random variables. Is this okay? Hello?
Yes, sir.
Right. I hope you're not, I mean, that's not, that was a weak yes, sir. I mean, I hope, you are like, this is what it is. Just, I don't have a pen, but I'm literally writing over here. Just imagine, forget about the ball also and squash racket also. I'm just writing over in the bracket, open curly bracket, close curly bracket, the number 1, number 10, number 25, number 1500, all of these are random numbers, right? All I'm saying is that each is a variable independent of the other. Okay, just stay with that. Is that okay?
Yes, sir.
Yes, sir.
Yeah. Now I'm just ramping this up a little bit. I'm saying that now let's call it as a Markov process. Okay, and what is a Markov process? A Markov process is again kind of a random process, but the future randomness is dependent on what I know now. The current value. The current value is all I need to know in a Markov process. Everything we know about the future is summarized by the current value. Just remember this. Just hang on to this. Hang on to this, okay? A Markov process is something, everything we know about the future. So suppose, the stock price for TCS is today 3,600. Then everything we'll know about TCS in the future is based on that 3,600. That's all. Don't apply anything that you learn. I'm just accept each of these statements as they are, coming to you. Just hear them and park them. Hear them and park them. Like, if you played Snakes and Ladders or Ludo, right? Have you played that game, right? All of you must have played that game, isn't it? Yeah. So just, like in Snakes and Ladders, if I throw a 6, I have to count 6. Similarly, if it's a stochastic process, this is what it is. If it's a Markov process, this is what it is. This is just a rule. Just park it there. We'll be using these rules to go to the Black-Scholes equations. That's why I'm telling these rules to you. Again, you don't have to know them in practice, but it's good to know that by using simple rules, Black and Scholes actually, they stood on the giants of other scientists and they created that equation. Okay, so stochastic process is number 1. Markov process is the second thing. The third thing, the term that I want you to know about is a random walk. Random walk is the price at n is, let's say, in 3 days time, is dependent on mu, which is the average price till now, plus the price at day 2, plus epsilon n, okay, which is an error term. Again, this is the third kind of a basic definition. Take it for its face value. It's a random walk that the price of TCS, I'm just using TCS for want of a better stock, and I'm saying the price of TCS tomorrow, okay, is dependent on the mean price of TCS till now, plus the price of TCS yesterday, plus a random term called epsilon. Nothing wrong in me forming this hypothesis, is it? I'm just forming a hypothesis. It is absolutely rock solid. Is it fine? Hello?
Yes, sir, it is fine, sir.
Yeah.
We got it, sir.
Yeah. And the last thing is martingales. So what is a martingale? So martingale is gambler's luck. How many of you have gambled? Can I see, do a show of hands? How many of you have gambled? Sarvesh is raised a hand. I don't know how many, only Sarvesh has raised a hand. So others have not gambled. How many of you played poker? But all of you must have, kind of thrown a toss, right? All of you must have thrown a toss. So that's gambling, right? Because you're throwing it to chance. I think people should try and play poker just to understand what poker is about, or teen patti, as they call, right? Or you can play even a game, like a simple game of there's lots of card games, but wherever there is chance, that is coming into picture. So gambling is whenever you kind of, like, let's say you toss a coin. You toss a coin, you get a head. You toss a coin again, you get a head. You toss a coin again, you get a head. Now somebody is betting with you that, I'm going to give you 100 rupees for every time you toss a coin. And you've been on a winning streak, right? Every time you toss, it seems that you're winning. Unlike, our captain who lost all his tosses, I think, in the T20 World Cup, right? So you're on a winning streak. So Martingale process just says that xn plus 1 will be xn. So if you won the last time, you'll win the next time. Simple definition. All of you with me? You all wish that life were like a martingale, right? Isn't it? Are you wishing it that way? Hello? Am I losing the class?
So could you repeat a question about something you mentioned?
Yeah, so Neil, all I'm saying is that, if you're on a winning streak, especially in the stock market, people always think they are martingales, or they are in a martingale process. A martingale process is that if you win, the next bet is also going to be a win. That's a martingale process.
Okay.
Sir, like hot hand fallacy.
Sorry?
So there is this.
Yes, you're right. It is the hot hand fallacy, but that's a behavioral fallacy. I'm giving you a mathematical proposition that there is something called as a martingale process. And that martingale process is nothing but xn plus 1, the n plus 1 as n plus first bet is equal, given there are x1, x2, xn, is nothing but x by xn. So if you have won on the xn time, you're going to win the next time. The expected value will be winning, the E, right? You may lose, but the expected value is winning. All of you with me? Hello?
Yes, sir, we are with you.
Okay, so let's go ahead now. You're seeing the screen, right?
We can't see your screen right now.
Oh shit, sorry. So these are the 4 things that we covered, not more. There are actually 2-3 more things, but I did not, because I think I would have found myself talking to myself. See, this is what happens, but I would like you to, embrace this with an open heart, because you're going to get an MSc in computational finance degree, okay, and you need to at least know these terms. I would appreciate if you actually go and Google them, be a little bit more familiar, and when you go and talk in an interview, or when you're talking with people, you can boast, I know what a martingale is all about, right? You can boast about, what is the Markov process all about, because these things will matter in your, not only in the financial market, but also in in your day-to-day life. This is the basis of many of the equations, especially Black-Scholes. Okay, so let's go to the next slide. So we are now going to discretized process, right? What is a discretized process? So the Brownian process is a discretized process. stock prices that you see, they appear as continuous, but are they continuous? Are stock prices continuous?
No, sir. They also move in discrete values, and that is decided by the market, the regulators.
No, they are ticks.
Yes, sir.
They are tick values. They are not continuous, right? So it's a
Yes.
I mean, forget about the regulator. They are ticks. So they are a discrete process. Option prices, they are discrete processes. Now, all we are saying about Wiener process is that the W of 0 of a Wiener process is 0. That's what it is. Just say that like any fx, like I'm saying f of 0 is 0. Suppose my fx is, or W0 is nothing but x square. All I'm saying is that x square, which is W of, I put the value of x as 0, and W of 0 then becomes 0. All of you with me? I'm saying my Wx is x square. I'm writing it over here. Assume that I'm writing W in bracket x is equal to x square. So my function is x square. All I'm saying over here is the W of 0 is 0. That's the nature of my Wiener process. Okay? Nothing much on that. And then I'm making a claim. I'm making a claim here. This is the important claim. What is the nature of my function W of tk plus 1? The nature is as follows. The k plus 1th tick for TCS, the k plus 1st tick for TCS, let's say tomorrow's TCS price, and I'm saying now there are thousands of ticks today. I'm just saying the first tick tomorrow. The first tick tomorrow is equal to the value of the last tick today, end of the day today, plus this is just a scaling factor, root of delta t. Delta t could be 1 upon 365 because we are crossing over. If you were to take delta t today itself, what would the delta t from the tick right now to next tick in 1 second? What will be the delta t? It will be actually nanoseconds. Can somebody tell me what will be delta t value? What will be the delta t value for 2 days? Suppose I'm taking WTK as a closing price and TK plus 1 as a closing price in 2 days. What will be the delta t value?
Sir, I'm very confused with your question, sir.
Okay, so I'm saying that this is just a function. I'm calling W of something as a function, correct? And I'm saying that W of 0, the property of this function is W of 0 is 0. This is simple, right? Any questions still here?
Yes, sir. I mean, no questions, sir.
Sorry?
No questions, sir.
No questions. Now the second thing I'm claiming rather, not even proposing, I'm saying that the W of tk plus 1, I'm having this bunch of numbers in a curly bracket. I'm saying the next number tk plus 1 is nothing but the value of tk, the last number tk, plus the time difference between the two numbers tk and tk plus 1, and the square root of that delta t into a random variable, a normal distribution z of tk. Now I'm saying that suppose I'm taking the closing prices of every day, today, yesterday, day before yesterday, tomorrow. So if I'm taking this WTK plus 1 is tomorrow's closing, this WTK is today's closing. So what is the value of delta t? And t is time.
So tk plus 1 minus tk, sir.
Yes. And what is tk plus 1? Tomorrow, which is 2. And
This
today
is
is
2 minus 1, 1. Sir.
Exactly. That's all I want. Perfect. So this is 1. Root of 1 is 1. And then this one, this is our familiar friend. What are we saying? This is a normal distribution. This is a random thing. So all I'm saying is tomorrow's closing price, W of Tk plus 1, that is Tk plus 1 is tomorrow, is a function of the closing price today, that is T of K today, that is today, W of Tk, plus root of 1, because actually it should be, if you are saying that T is 256 trading days in a year, we should take root of 256. But don't worry, I mean, we can still say 1 just for the sake of understanding. It's a scaling factor. And then here we are saying this is the random variable. So this randomness will throw everything into a random, this will be a random value. Okay. The third thing I'm saying now, if I want to take a difference between, if I define my functions in such a manner, W of 0 is 0, this is true, then if I want to take a difference between these two values, say I call K plus 1 as L and Tk as K, then what do I have to do? In between these two intervals, I have to sum up all those things, right? I have to sum up the little values, WTK, the values of this across this spectrum, right? If I want to, so I'll have to sum up this thing, this small thing. I'm just doing a simple math here. I bought this WTK over here, W2L, and I made it as WTL minus WTK, correct? And in the right hand bracket, I'm just saying I've got this, but now summing it up from K is equal to 1 to L minus 1. All of you with me?
Yes, sir.
Yeah. And when I sum it up, a beautiful thing happens. Since the mean of this thing, this distribution is 0, and the variance of this ZTK is 1, if I sum up all the variances, they become what? They become 1. And then I sum it up from L is equal to K to L minus 1, I get it as L minus K. The variance of TL minus Tk becomes L minus K, actual value of L minus K. And since this, since all of this, the mean is 1, so what I get is that the mean becomes 0 and the variance of this term becomes L minus K. Okay. It's okay when you actually try to write this down, right, with actual numbers, you can prove it to yourself. All I'm saying is that I claim this, it's not I. There's this gentleman called Weiner who's invented so many difficult mathematical things, and you are using it in practice on your mobile phones currently but not knowing about it, but it's a Weiner process. So the Weiner process is defined by this thing, that the value of Tk plus 1 is nothing but the value of Tk, which is yesterday. For our convenience we said yesterday and today, root of delta T into Z of Tk, a random variable. And all I'm saying is that if I just take a difference in these two, WTK plus 1 minus WTK, and I sum it up, I get this. And then I try to take a mean and variance of this, I still get the mean as 0 and the variance as L minus K. Sorry, I did not write it over here, but the variance will become L minus K as you add it over these terms. Okay, so that's all I'm saying. I'm saying nothing else. So let me go to the next slide now. Anybody totally uncomfortable with this for a moment? I just want to take a 1 second thing. Uncomfortable with whatever I have said. Hello? Anybody with a major botheration? Can I continue? Ali, Neil, Mihir,
Sir, I'm fine
Prasun,
with it, sir.
you're fine. Everybody else is fine. No major problems. No major problems, right?
No problem, sir.
Yeah. Okay. So now let's move on to the entire allow. So now I'm going on to the thing. Okay, so now I've defined what a discretized process is. The problem with the discretized, we've defined what a discretized process is. Now I'm going to Brownian motion, right? Imagine Roger Brown in the 1800s, you know, observing pollen and then seeing, oh, they're floating. Why are they floating? Like small particles. You must have seen those particles, like in a bright jab of sunlight. You must have seen lots of particles, right, just floating around. So Robert Brown must have wondered what is happening, and then these people, Weiner has tried to put a meaning to this. We just saw that WT minus WS, we saw WL minus WK. It is normally distributed with mean 0 and variance as T minus S. Okay, the variance is T minus S. We saw that it is L minus K, right? We saw that this is L minus K as is summita, and the mean is still 0 because we are subtracting the mean. We are subtracting this from this, so mean of that is 0. And the mean of this is 0. The 0 into this is 0, so that's why mean is 0, and the variance will become L minus K. So in the Brownian motion, we now say that Brownian motion, this is normally distributed with mean 0 and variance as T minus S. Just a nomenclature, time T, time S. And we just saw that W has independent increments. That's how we define what a random process is, right? So what do I mean by independent increments? The price of TCS tomorrow and the price of TCS today, I minus that. The price of TCS day after tomorrow and the price of TCS tomorrow, I minus that. All of these values are independent increments of each other. Completely random is what we are saying. And then we know by definition, we saw that W0 was 0, right? W0 is 0. And WT for all t greater than 0 are continuous functions of t. I'm not going to discrete now. I'm going to, a Brownian motion. They are continuous functions of t. No more ticks. No more ticks. They are continuous functions of t. And once I define this, that becomes the Brownian motion. This is what Brownian motion is all about. That's it. These are the defining characteristics of a Brownian motion. I'm not going to ask you this in the exam. Probably nobody will ask you in the exam, but know the basics. Listen to them, make them resident. Listen to all the terms that I just shared, make them resident. If you go to if you wanted to earn $1 million in salary, you will need to be comfortable with these terms. Not only comfortable, understand them deeply. That's what option traders do. You've read Nassim Taleb, right? Anybody who has not read? Okay, how many of you know about Nassim Taleb? Shubham has raised his hand. Many of you raised your hands. So if you want to, that's what, he would have done hundreds of times, stirring the pot again and again. And, it's not rocket science, really. People who were really rocket scientists invented this stuff. All we are doing is, reusing material that was done hundreds of years ago. Okay, so just be comfortable with them, bear with them, pay respect to that. So this is Brownian motion, and we take Brownian motion, and this is what we get. I took exactly the formula that I gave you, and you will do it in practice, and I'll share the Python program with you today, and run the Python program. I just took the TCS price, and this is what I get for the TCS price based on the expected return and the standard deviation for the last 1 year. There's one problem with Brownian motion. There are many problems with Brownian motion. But can somebody tell me that, if you are able to do a derivative of this over here? Can you do a derivative of a Brownian motion graph? What is the essential thing for doing a derivative? Let's go back a few slides. Because this is the concept. I'm not asking you to learn maths. I'm just saying, what is a derivative? This is a derivative. This is a curve. let's even not touch the maths. What is the difference between this curve, and the curve we just saw? Somebody? Anybody?
Yes, so could you repeat the question of what do you want from the graph?
So my first question is, can you take a derivative at any point in time on any of these curves? There are 500 curves here.
I mean, theoretically, yes, you can take a derivative, I'm sure.
I'm saying all of these are Brownian motion curves.
Sir, also it's discrete. So given it's discrete, the derivative might not even exist.
No. So sorry. So I changed it to Brownian motion, right? So this is not discrete anymore. So it's
Okay.
Yeah.
They're continuous.
Yeah, they're
Yes,
continuous. But it's a
yes,
Brownian motion.
The derivative does exist.
Yeah. So Neil, that's the issue, right? So the problem is, for derivatives, what happens is, what you need to do is, for derivatives, you need to have a tangent. And even before that tangent, when you draw a derivative, what really happens is that on this x-axis you take small increments dx, and for that small increment you find out y. Okay, that is what the derivative is, right? What is the derivative of this? When we are saying this, what is the derivative? We are treating, and we are making this dx approach 0. What is the value of y, the dy, as dx approaches 0? And by definition, in Brownian motion, this does not exist. Okay, so that is why, by definition, in a Brownian motion, you cannot take a derivative. Okay, so if you try to take the derivative of this, these are all independent increments, right? So as you try to take the independent increments, there's a problem. And the inability, even if without going into the maths, you can look at the curve, right? So you can look at these curves. You just can't take a derivative. You can't take a derivative here, because you don't know. It just goes in a random direction anywhere, right? Suppose, without going into Newtonian deep calculus, I'm just saying, try to find out some points where you can find out the slope, but you can't, right? That's why, we have to go to Ethos. Remember the triangular thing that we saw at the very base level was, our normal calculus. Then we are now going into stochastic calculus, where we are trying to find a derivative, but we can't, for a Brownian motion in play. And since we can't do that, we'll have to resort to something else. So this is the proof that it is not differentiable. Okay, this is the proof. It's easier to look at squares, right? It is easier to look at squares. So let's say if you just say Wt minus Ws and we square it, and we're doing expected value, right? Since the expected value of this is, what is the expected value of this? As t minus s goes, I'm not even saying t minus s is going to 0. I'm doing a square of this. Right? So we saw that we are talking about the variance now. We are taking the second moment, right? And we saw that it was just simply t minus s. So t minus s divided by t minus s square. What is that? 1 upon t minus s. Now 1 upon t minus s will go to infinity as t minus s goes to 0. You agree with this, right? So this is the maths, but this is the practice. When you try to actually go and take a dy by dx, it's simply impossible. That is why you cannot, it is not differentiable. That's the quirk of a Brownian motion. And the second thing about the Brownian motion is that it's a Markovian process. It is defined by where you are starting. They are all random. So I've just generated 500 paths. There could be 1,000, there could be 10,000, and so on. What is a Markovian process? Markovian process, everything is dependent on the starting point. Right? That's a Markovian process. And then there is a Martingale property. The expected value of the next thing is dependent on the last thing for all t greater than s. And you can actually prove the Martingale property. You can prove the Martingale property by this. I mean, you can, I mean, those, especially Kriti, I think she's done her maths. You can actually prove the Martingale property without any fancy thing. There's no derivatives, there's nothing. I'm just taking E of the expected value of the stock, W of t, as E of W of t conditional of W of s. Correct, there's nothing wrong in that. Expected value of W of t at time s. And then I'm saying that at time t is nothing but conditional of W of s, because that's what we said the Markovian process is all about. But this, in fact, is nothing but E of W of t minus W of, I'm just adding and subtracting W of s. And then you can cancel these terms, and then you can get W of s. And then you can prove that this is a Martingale. So you can prove that a Brownian motion in play is nothing but a Martingale. Okay. So this is some heavy maths, and I'm, but forget about the maths. Totally forget about the maths. What I'm saying is focus on this. Focus on this. Those who are mathematically inclined, of course, they should go and actually, try to at least crunch some numbers. You'll find it fascinating. Focus on this. This is what we've covered so far. We've not gone here. We have not gone here. We have taken calculus. We just said that we need to have a separate branch of stochastic calculus because we can't use the normal rule of dy by dx. So let's find out what the Ethos rule is. Okay. Sorry. I hope you don't mind me continuing. How much time do I have? We lost 15 minutes in the beginning.
So it's almost 1:30 now.
But we lost not 15 but 10 minutes in the beginning, right? So can I continue for 5-10 minutes more?
Yes, sir.
Yes, sir, you can continue, sir.
No. So only if this is useful to you. Otherwise, we can. I mean, see, there's no way that you will be able to understand. I mean, of course, you can understand Black-Scholes. You can, of course, understand Black-Scholes, right? Anybody, I mean, you can give it to a 12th standard kid, and tell that kid, okay, mug this up, and you'll understand it. But if you wanted to know why has Black-Scholes happened, you'll have to think about the problems in the stock price that you're seeing, right? And options are based on those stock prices. So people were trying to model what the stock prices were, and when they started modeling, they discovered that you don't have the luxury that that normal calculus gives you. That's why I just brought into picture Brownian motion. And Brownian motion, all that Brownian motion is saying is that that you cannot do a derivative at any point in time on the Brownian curve. Brownian curves have got some more properties, but let's not go into those properties. Let's go back now. So ordinary differential equations, is something that we saw, right? What are ordinary differential equations? You're taking the derivative of function, let's say x of t, or let's say the stock price, and you're taking a derivative of this, and then you're saying that this function x of t is actually nothing but mu of t of xt. Think of this as the option price, okay? Think of this as the option price. And the option price has got two components in it. One is the time, and one is the stock price itself. No disagreement there, right? There's no disagreement here. So ordinary differential equation, we just say that, say d of xt, the incremental change in the value of the stock price can be written as, I just took this dt and I multiplied it here, I think as dt into mu of t of xt. Correct? Nothing fancy. I just took this, I took this from the denominator, multiplied it, and that's it. Now this is the thing that let's jump from normal calculus to stochastic differential equation. What it does is that it says d of xt. So this entire term over here, how can I change my cursor to give me 1 second, pointer options. So the entire term over here, right? This entire term is exactly as this term, right? Exactly as this term. This term is exactly as this term. I just took this d of xt is nothing but mu of t of xt, right? And I just took the dt from here and multiplied it here. I said d of xt is equal to dt of mu of xt. So this term is exactly the same as this, no change. But in a stochastic differential equation, we add this. We just say we add this term, this sigma of t of xt, sigma or t of xt, and then we say sigma in, and then we say, and we multiply it by d of wt. That's the only thing that we do. Okay. And if we integrate this, how do we integrate this? Simple integral over here, integral over here. In integral form, we say, because we are integrating it from x0, x is equal to 0 to x is equal to t, x of t is equal to x of 0, the beginning value. This is a standard calculus integral from 0 to t mu of s of x of s ds, right? This is, I'm just changing t to ds. And this is the stochastic integral. Same thing, I'm taking this term and I'm integrating it. So you're comfortable with this? No, nothing fancy. Nothing fancy, right? Neil, Shubham. Nothing fancy, are you? Yeah.
Sir, can you again, sir, repeat the third point, sir?
So what I'm saying, in a stochastic differential equation, in a normal equation, first of all, forget about this part. Forget about the lower half. Forget about this part. A normal differential equation. And why the hell do I want to do the normal differential equation? I am saying that my option price is a function of the change in option price, like let's say the delta, but it's a function of the time t and the stock price, right, which is also a function of time. This is what I'm writing, right? So this is a normal differential equation. I can just differentiate it, right? But it has got two components in it. The first component is time. The second component is the value of the stock price. So in a normal differential equation, when I differentiate it, I just have this piece. And if I want to get the value of d of xt, I just get the dt over here and I form this. Are you okay?
Yes, sir. Yes, sir.
Yeah. So that's all I did. I did nothing fancy. All I did was I took this dt from here. And I got the dt over here. That's all I did. And then I got this, right? I got this thing. All I'm saying is, in the when I want to transform this to a stochastic differential equation, this is what all the great people have said, that in addition to this, you add this term. Okay, this term. You add this term. That's all I'm saying. I'm saying nothing else. They said you add this term to make it work. Sorry, this is the best I could draw with a mouse. And then when I integrate this, when I do an integration of this from 0 to t, when I do an integration of this is what I get. And till this part, everything is same. Everything is same till this part. Okay. This is the part when things are different, and this is the stochastic integral. Is what I am saying. Is that okay?
Yes, sir, that's okay.
Yeah. So now I'm going to the next part. So this is a differential equation, and I'm just converting that differential equation. I took that as the basis. I'm demonstrating that this is what happens in the normal in the stochastic differential equation. And why stochastic? Because it is a Brownian motion. And in the Brownian motion, we need to, otherwise our results will be wrong. In the Brownian motion, we have to take stochastic or random. We have to assume that every state of the price of TCS is going to be random. Okay. Now we go to the next rule. So this is Ethos rule. What Ethos did was he took standard calculus. He did this standard calculus like d of dt, f of txt. Right. So this is, let's say, the stock option price, which is a function of time t, and the stock price is x. Then if you take a partial derivative of this simple, the first term, you can go back to any standard, you can Google this and get the standard partial derivative rules. So for taking a partial derivative of these two functions inside a function, you take the partial derivative of f of txt by dt, plus you take a partial derivative of the second variable d of dx, and derivative of this function multiplied by the derivative of this, a simple derivative of this, not partial, of xt. And there's a notation for writing this. We just say that d of txt is nothing but the f prime txt, f prime t txt plus f prime x txt into dxt. Now what Ethos did was he took the same thing. Okay, he took the entire same thing, and he did it for a different purpose. As we talked earlier, I forgot what purpose he did. He took the entire same thing. This part is exactly the same. Oh my God, sorry. This part is exactly the same. He took that part. The only thing he changed, he took this part. The only thing he changed, he added this. In stochastic calculus, we already saw that, right? We already saw that he added this. And then when he said that when you want to do a derivative of this is what you get. So instead of this ft of xt, f prime t xt plus f prime x txt dxt, that is this term, in addition to this term, he said you need to account for one more term, which is one half of the double derivative of x, t of xt dt. Just for what it is, right? Just treat it for what it is. So this is Ethos rule. Okay, so this is Ethos rule, and also called as Ethos lemma. And if you solve this using these values, if you solve this, you get this in a nice form. D of f is equal to f prime t plus mu of f prime x plus 1/2 of mu rho square f second derivative of x into dt plus sigma of f prime x into dw. So this is what you get. That's it. Now, what Black and Scholes did was they took this piece. And they tried to, first of all, Merton, right? I mean, Black and Scholes were there, but Merton did not get Merton did get the Nobel Prize. Fisher did not get the Nobel Prize. So what Merton did was he tried to find the delta of an option. And what is the delta of an option? Delta of the option is the change in the value of the option given the stock price, right? So he got the delta of the option as this equation. And this equation has lots of assumptions, but still people found it to be valid. It was a valid thing to do. And let's just cover the assumptions before going into Black and Scholes. And if you're patient, maybe we can cover Black and Scholes. Shall we cover Black and Scholes, or you want to stop in the next 5 minutes? Hello?
Yes, sir.
Sorry? So you want to stop in the next 5 minutes or cover till Black and Scholes?
Sir, let's stop in 5 minutes. Oh,
Okay, so you want to stop in 5 minutes. So, so the Merton's derivation, right, which is an important piece of Black-Scholes model, right? It has got several assumptions which need to be really looked at very carefully. First assumption, stock price follows a geometric Brownian motion. We already covered what a Brownian motion is. Geometric Brownian motion is just that, the term that we saw, the row term that we saw, it follows a geometric path. The second thing that he said was there are no dividends. So this was for options, and he considered that dividends are zero. Then he also said that trading is always continuous, which is not the case, especially when you go to illiquid stocks, when you're doing that in India. Then he said that short selling is not allowed at all. Now this rule is never valid in India, because in India, as you know, there's a huge short selling. And how do you do short selling in India? Can somebody tell me? How do you do short selling in India? Anybody?
Maybe with using futures.
Absolutely. In India, we don't have a very liquid stock lending market, but what we do is we do short selling using the futures. The single stock futures are arguably the most liquid in the world today. And then there are no transaction costs. Securities are infinitely divisible. There's no riskless arbitrage opportunities. Term structure of lending is flat. So, if I lend for 1 day, if I lend for 30 days, if I lend for 1 year, it is all the same. And there's unlimited borrowing and lending. So there's lots of ifs and buts in Merton's derivation. But this Merton's derivation leads us to the Black-Scholes model. So, I think, folks are, kind of saturated at this point in time. But I think this was the most difficult part in the journey so far, when we are doing options and Greeks. Okay, I hope from now on we'll use more of practice. I'll do one quick poll and to assess, where we are, and then I'll let you go. Was this pace too slow, too fast? Please grade me on a scale of 1 to 5. 5 being the fastest. One, 2, 3, 4, 5. Feedback is good. Okay, so I've got the median people are saying that this is okay. I'm at space 3. So what I would do is today I'll give you a bunch of Python programs. Who can I send those Python programs to? So that all of you have got Jupyter notebooks. We'll start to, get things into practice, enough of maths, right? Do you want to do some fun with Python before tomorrow? Hello?
Yes, sir. You can send the codes to Sahaj. We'll give her email ID.
To whom?
She's a CR, sir.
So can the CR please send me their Gmail ID or whatever ID? Just chat over here or send it to me on email. Okay? All of you good? Hello?
Yes, sir. I have sent an email ID.
Okay. So I should send a mail or you send me the email ID?
But if you want, you can leave your email ID in the chat box. We can ask her to contact you also.
My email ID. Oh, she's not present. Okay, one second. Where do I chat?
So bottom right corner, there's a chat box.
Yeah, why don't you put her email ID here? Oh, it is sahas.manocha at this one? I got it, Neil. Thank you. It is sahas.manocha@gaip.ac.in, right?
Yes, sir.
Right. Thank you, Stuti. I hope all of you have installed Jupyter. All of you have Jupyter Notebook or Anaconda, or how are you using your Python, or are you doing it in Google?
Most of us have Jupyter Notebook because that is how we were taught in the previous semester.
Fantastic. Okay, fine. So let's do some practical things. Going forward, there'll be some bit of maths is left, I'm afraid, because you've not covered Black and Scholes. But after that, the maths is you've at the peak now, and now it's all downhill. Hopefully. Okay. Cheers. Thank you.
Thank you, sir. Thank you so much, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Bye.